Okay guys, so in this video I'm going to run through as much as I can of a practice test 1 in about an hour. So this first problem here is about interpreting an energy diagram. So you're given the energy diagram that shows the allowed energy levels of an electron in a particular atom or molecule, and you have to identify various things. So the first thing it says is which is the ground state, and hopefully you know now that the ground state is just the lowest one. So that guy is the ground state A. Now anything that is not a ground state is an excited state. So there can be only one ground state but multiple excited states. And in this case there is 1, 2, 3, 4 excited states. So they then ask how many lines are in the absorption line spectrum. So when light is absorbed, electrons move from lower energy levels to higher energy levels. So there will be a bunch of transitions from the ground state to excited state. So there are 4 of those guys. And then you're going to get some from the first excited state to the higher excited states. And there are 3 of those. And then we're just going to kind of keep going in that way. So we've done that one, and we've done that one. Now there are those that begin at the second excited state. So there are 2 of those. And then finally, there's one that begins, we've done that guy, at the third excited state. And there's just the 1 of those. So there we go. 4 plus 3, that's 7, 9, and there are 10 lines that we would expect to see in the absorption line spectrum of this particular species. Okay, so tallying those up is not too bad. And then it says, what transition causes the absorption line at the shortest wavelength? So shortest wavelength is just code for biggest energy, which is just code for the biggest distance. So the biggest distance that an electron could move when it absorbs light, so remember you've got to be careful with absorption and emission, absorption is going up, would be when it goes from A to E. Now that's an absorption. If you said from E to A, that would be emission. So keep that in mind. So that one there is the one with the biggest energy or the shortest wavelength. Now, the next one says, what transition causes the absorption line at the longest wavelength? So, longest wavelength equals smallest energy, which is equal to the smallest distance, right? So, that's going to be between B and C. And again, because it's an absorption, you've got to be going up. So, B to C. So keep an eye on this keyword in the middle here. If it was an emission, we've got to be going down. If it's an absorption, we are going up. So be careful of that. Sometimes people get those letters around the wrong way, and Alex would like you to use the uppercase letters, just like it is labeling them with the uppercase letters. Okay, this is all about understanding how wavelength and sort of the written description of light is related. So this is what we call the electromagnetic spectrum. And so what you have to realize is that we have gamma rays, and then we get X-rays, and then we get UV, and then we get into a range of colors that are called the visible, and they have a particular sequence. There is violet, indigo, blue, green, yellow, orange, red. That's the visible. Then beyond the red we get the infrared, and then we get a microwave, and then we get radio. And wavelength increases in that direction, and frequency decreases in that direction. So you just got to take your time, and in this case we're going to order them by increasing wavelength. So number 1 is going to be the shortest wavelength, and then we've got 1, 2, 3, 4. Number 4 will be the longest wavelength. So we want it, the shortest wavelengths are going to be down this end. So as we go through here, what one's going to have the shortest? We've got red light, blue light, radio waves, infrared. It's got to be blue, isn't it? So blue is going to be my shortest wavelength coming in at number 1. And then my next one along, it's going to be number 1, would have to be red. All right, that's going to be number 2. And then it should be infrared, will be number 3. And then finally, number 4 is going to be radio waves. So blue, red, infrared, radio waves, wavelength increasing in order of increasing wavelength. So that looks good. So 1, 2, 3, and 4. Now there are images of the electromagnetic spectrum, and quite a lot of you guys, I kind of encourage you to include this in your notes for this particular section. I'm like, hey, you probably should put that picture in there, but you know, have a look in the book, and it has a diagram with all of the electromagnetic spectrum pretty clearly labeled. Okay, so this question looks like it's going to be a unit conversion problem. So it says humans have 3 types of cone cells in their eyes which are responsible for color vision. Each type absorbs a certain part of the visible spectrum. Suppose a particular cone cell absorbs light at a wavelength of 569 nanometers. Calculate the frequency of this light. And you're meant to give your answer in terahertz. So I went to the data section, and the very first table are these SI prefixes. So when we have prefixes that correspond to powers of 10 with a positive exponent, they're on the left, and then prefixes that correspond to powers of 10 with a negative exponent, they're on the right. So we've got 2 exponents in here. We've got tera and nano that we're going to be needing. So first we've got to take this wavelength, turn it into a frequency, and make sure that it has the correct units in terahertz. So what we know is that the speed of light is equal to the product of the wavelength of light and its frequency. So what I can do now is that the speed of light divided by the wavelength is equal to the frequency. All right, so let's give that a go. So it's 2.998 by 10 to the 8 meters seconds to the -1. That's the speed of light divided by this wavelength, which is 569 nanometers. Now I want to be cancelling meters, so I'm going to be using the prefix for nano. So how I'm going to do that is just quite simple, 569, and then instead of writing the n, I'm just going to write times 10 to the -9 meters. And when I do that math, you can see that it's going to leave me with units of per second. So let's go ahead and do that like right now. So 2.998 by 10 to the 8 divided by 569 by 10 to the -9. So speed of light over the wavelength. And you've probably heard me comment before that typical frequencies that we're looking at should be around 10 to the 14. That's pretty typical, and this is per second. Okay, so what you need to keep in mind is that 1 hertz is exactly the same as 1 wave per second, but now we need to turn this into terahertz. So hertz on the bottom, terahertz on the top, and 1 terahertz according to this is the same as 10 to the 12 hertz. And then hertz per second leaves me with terahertz, so I know I've got it correct. So I'm not rounding anything. I'm going to go in here and I'm going to times 1 divide 1 times 10 to the 12. There we go. So very cautious. So it ends up being to 3 significant figures as asked, 527 terahertz. Okay, there we go. Pretty straightforward. Interconverting wavelength into frequency. Here's our key formula, and then the rest is just doing unit conversions using decimal prefixes. All right, not doing too bad. We got through a couple of questions in like around about 10 minutes, so that's really good. So we're cruising here. It's always nice to build up a bit of buffer of time in case you hit a difficult question, and also you want to be checking everything very closely. All right, this is interesting. You're given an energy level diagram, but you actually have the energies actually numerically marked on the y-axis. They're in these zeptojoules, so tiny little amounts of energy. 10 to the minus 21 joules is a zeptojoule. And then you just have to answer various questions, all right? So read the scale carefully, make sure you're not making any errors. So it says, what is the energy of the electron in the ground state? Well, that's the ground state there, and we just want to zoom in, make sure we get it right. And it's pretty clearly 200 zeptojoules. And then it says, what is the energy in the first excited state? So this is the first one, and this is the second one, so we want this energy. And so we just, again, make sure we don't read the scale incorrectly. So there's 400, 450, 500, 550, 600. So I'm pretty convinced that this is 500 zeptojoules. Okay, that's good. No mistakes there. Okay, so now we're going to do this transition. If the electron makes the transition shown by the red arrow from B to C, will a photon be absorbed or emitted? So a photon is absorbed when an electron goes from a lower to higher energy level, and when an electron moves from a higher energy level to a lower energy level, a photon is emitted. So in this case, we're going up, so it must be absorbed. And then now we need to calculate the wavelength of the photon that would be absorbed or emitted in the above case. And we're going to give this to 3 significant figures in nanometers. So what we've got to do is calculate the change in energy, and then we're going to use our little formula that the change in energy is equal to hc on lambda, and we'll organize and solve for the wavelength. Now we'll have to do a little bit of unit conversions right at the very end to get it into nanometers, but it should be pretty easy. So what's the change in energy? Well, we're going to start at 500. We already figured that out, and we're going to go up to, there's 800, 900, 950. So I can do this in my head. There's been a change in energy of 450 zeptojoules. Okay, so we need to keep in mind that zepto means by 10 to the minus 21. So we're going to keep that in mind when we do this. So reorganizing this to solve for wavelength, is it going to be equal to hc on delta E? So Planck's constant, 6.626 by 10 to the minus 34 joules seconds times the speed of light, 2.998 by 10 to the 8 meters per second, divided by the change in energy, 450 times 10 to the minus 21 joules. Now remember that a wavelength should be a length, right? So we want to have units of length at the end of this process. So joules goes, seconds multiplies by seconds to the minus 1 is going to cancel, and all we have left is meters. So this will give us our wavelength in meters, and then we got one more step, which is convert it to nanometers, which we can do like that. So let's do the first step. Planck's constant, 6.626. Second function, E. Ooh. My touchpad on my laptop is a little wacky, and I'm at a conference at the moment. Normally I'd be using like a plug-in mouse, and so sometimes I miss hitting buttons using the little trackpad. So bear with me. Even more klutzy than normal. Okay, that's my top line. So Planck's constant times the speed of light divided by 450 by 10 to the negative 21. So very small number. Okay, so there it is in meters, and you know the wavelengths of light are normally very, very small, right? So 4.414 by 10 to the minus 7. 4.414 by 10 to the minus 7 meters times 1 on 10 to the minus 9. You see meters will cancel and it'll leave me with nanometers, which is what they wanted. So let's see what we get now. Times 1 divide 1 second function e minus 9. There we go. There it is, 441 nanometers to 3 sig figs. Okay, so remember that your violet is around about 400 nanometers, and then your red is about 700, depends on how your eyes work. So this is going to be kind of looking pretty, it's going to look blue, you know. This is what I would say. It's going to be like, you know, indigo blue. So in that bluish violet end of things. All right, so 441. Nothing too bad. Too bad. Nothing horrid at the moment. Okay, this one looks like we are going to be ranking wavelengths again. So, you know, what I would suggest for this kind of thing, go to your book. Go into the chapter. It's in the very first section. And here's your diagram, okay? And then it gives a little expansion of the visible region. And it's all labeled increasing energy, increasing frequency, increasing wavelength. So as long as you read that, you know, carefully, you shouldn't be making a, you know, you shouldn't be making big errors on this. So let's just be really careful. So these are our short wavelengths down here. We got gamma, then we got X-rays, and we got ultraviolet, and then we're into the visible, which goes violet, indigo, blue, green, yellow, orange, red, and then we go infrared, microwave, and finally radio. So my diagram doesn't look quite as good as the one in the book, but it does the trick. So now we've got to list them in order of increasing frequency. So frequency increases to the left. So we're going to start on the far right and work towards the left. So let's see what we've got. Well, microwaves is going to come in at number 1. Then our next one is going to be red, coming in at number 2. So 1, 2. And then we're going to have blue at number 3. And there's only one left, which is X-rays, and that's got to come in at number 4. And that will be increasing frequency. So that looks good to me, and I just double check that and make sure that I haven't made any, you know, stupid errors. And yeah, that'll be good. All right, this is looking at possible quantum numbers. So you have to list out the possible quantum numbers. It looks like we're going to put them in separated by commas for an atomic electron with principal number n equals 5. So that means we're in the 5th shell, right? So it would be in the period 5 of the periodic table. What kinds of electrons are possible? And so what we know about L is it's going to run from 0 in increments of 1 all the way up to n minus 1. And n minus 1 in our case is going to be 4. So the possible values of L are going to be 0, 1, 2, 3, and 4, right? Because n minus 1 is 4. So what do these kind of correspond to? Well, they're like S, P, D, F, and these are kind of just mathematically possible. We would call them G orbitals. And what we actually find is that we never actually need to go that high because we don't need to have that many electrons in the 5th shell. All right, so the 5th shell is right at the bottom of the periodic table, and we know for certain that there are definitely F subshells for elements that are in that 5th row. So let's have a look here and I'll show you what I mean. Maybe I can't click on that. It's not working the way I want it to. It's fine, we won't bother doing that. So I hope to hyperlink these things, but I didn't do a good job of that. All right, let's have a look. N equals 6, so this is the 6th period of the periodic table. So remember that L is going to run from 0 in increments of 1 all the way up to n minus 1. So n minus 1 in this case is going to be 5. So L would be 0, 1, 2, 3, 4, and 5. They are the possible values of L. It's pretty straightforward, isn't it? All right, so there we go. Okay, this one looks like we're talking about that section, periodic properties. And we're going to arrange the atoms here in order of decreasing size. So decreasing, so biggest to smallest. Right? So what do you want to get? We want to know the order that they get, bigger in, right? And it turns out that the atoms increase in size as we go that way. So they increase in size. Okay. All right. So, and we want to go from biggest to smallest. So the biggest one of these three is going to be the one that is furthest left and lowest in the periodic table. So what do we got? Oh, we've got neon, we've got carbon, and we've got oxygen. So this is actually pretty easy because they're all in the same row. So we just have to remember that they get bigger as you go that way, and they get bigger as you go that way. So as these guys are all in the same row, we know that the order is going to be carbon, oxygen, neon. Carbon, oxygen, neon. Okay, there you go. All right, so that's not too bad. Just got to make sure you don't get your order reversed, right? As long as you don't get your order reversed, you're okay. I should point out all of those guys were neutral atoms, and that made it a little easier. So now we're going to draw the electron configuration of a neutral atom of nitrogen. So nitrogen's got 7 electrons, so its electron configuration is going to go 1s2, 2s2, 2p3. So we know that we've got this right. There are 7 electrons. Its outermost shell is number 2, and it should be the 3rd member of the p block. 1, 2, 3, and it is. So got a good shorthand electron configuration there. Now I'm going to translate that into a diagram. So I need one box indicating the 1s, and I'm going to put 2 electrons in there with opposite spins. Then I need a box at higher energy that represents the 2s, needs to be labeled appropriately, and then again I'm going to put 2 electrons in there with opposite spin. Now I need a set of 3 boxes, and that represents the 2p subshell. And then when I put the electrons in, I put 1 electron with up spin into each of the boxes. Remember, we don't start pairing up in a subshell until every orbital has a single electron in it. We always put the first electron in directed up by convention. And so that's it, right? So this guy's got 3 unpaired electrons in the 2p subshell. Okay, all looks good to me. Everything is in the correct order in terms of energy. Yep, we're all good. Okay. Now, this one here is not too bad. What you have to do here is they're giving you a condensed or abbreviated electron configuration for some kind of hypothetical element, and then you have to decide whether it's a metal or a non-metal. So you'll be wanting a periodic table like the one in Alex that has everything color-coded to make that easy. And then you have to decide, is my atom in the SP, D, or F block? So that's the S block, this is the D block, this is the P block, and this is the F block. So what block it's in is pretty easy to tell. You're just going to look at where its outermost subshell is, right? And so you can see that the first 2, the outermost subshell is the P subshell, so they're in the P block, and then in the last one, its outermost subshell is in the F block. So there we are. So easy going. Woohoo! And then now we have to decide, is it a metal or a non-metal? Now at this point, you're going to look at the number, right? The last number. So this is going to be in the 5th position in the P block. 1, 2, 3, 4, 5. So there it is. Now we know that from 6 and 7 onwards that we have F electrons, and this abbreviated electron configuration doesn't have any F electrons in. Actually, it doesn't even have any D electrons. So from 6 and 7 onwards, you get F electrons. From 4 and 5 onwards, you get D electrons. So in fact, the elements that we're interested in are just those two there, fluorine and chlorine. So they are both non-metal, so we're just going to circle the non-metal box. All right, now the next one is interesting. We have D electrons, and our element is in the P block, and it's the 6th member of the P block. So 1, 2, 3, 4, 5, 6. So it's in here, but it has D's, but not F's. So the first 3 rows don't have any D's, right? So that cuts it down to there because we needed to have D's. But then rows 6 and 7 have D's and F's. So that cuts it down even further. So it's just those 2 elements, and both of those elements are nonmetals. Okay. Now P block is kind of hard to figure out because, you know, P blocks, it could be a metal, metalloid, or non-metal. It's kind of, P block is all over the place. D block, S block, and F block, they're always metals, and you don't have to think about it, all right? So when I see F block here, I automatically know that this is going to be a metal, and it doesn't really matter. But what I want to see here, it says NS2MF10. So these would be the elements. They don't have D's, so this is where we kick in. So this is going to come down here, and it's going to go to the 10th member of the F block. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it's those 2, right? And those 2 are the ones that we're talking about, and they're both metals. Now anything in the F block is a metal, anything in the D block is a metal, anything in the S block is a metal as long as it's not hydrogen. All right, so pretty straightforward. Okay, that's it. Slow and systematic, and it'll be okay. Now, this is kind of some of the newer stuff. So it says, decide whether this proposed Lewis structure is reasonable. So yeah, to check a Lewis structure, you've got to do 2 things. The total number of valence electrons is correct. Okay. And then the next thing is that each atom has a noble gas configuration. Okay, and you want to check them in this order because it could have this, but this would be wrong, right? So you know, you want to be the, so I like to check it in this order. So what do we mean by having a noble gas configuration? It means that every atom that is not hydrogen has a share of 8 electrons around it, and if it's hydrogen, then it has a share of 2 electrons around it, like helium. So how many electrons have we got here? So you need your periodic table up because your number of valence electrons for a particular atom is just equal to the group number. So we have got Cn minus, that's our thing. So carbon is in group 4a, so it contributes 4 electrons. Nitrogen is in group 5a, so it contributes 5 electrons. And then we've got 1 negative charge, so we have to add in an electron for that. So for polyatomic ions, you add in 1 electron for every negative charge, and you subtract 1 electron for every positive charge. So that means we've got 10 electrons total. So now what I'm going to do is see whether this structure has 10 electrons. 2, 4, 6, 8, 10. So it has it meets the first requirement. The total number of valence electrons is correct. Remember, every line represents a pair, 2 shared electrons. So keep that in mind. So when we're counting up lines, we're counting up 2 electrons. Okay, so it has the right number of electrons. Now we have to decide, are they correctly distributed? And so that means that we don't have any hydrogen atoms here, so every atom here needs to have 8 electrons around it. So 2, 4, 6, 8. So the nitrogen looks good. But when we go over to the carbon, 2, 4, 6, and the carbon doesn't have an octet. So if you wanted to make this good, what you'd have to do is, remember, bring in lone pairs making multiple bonds, and it would look like that. So it would end up with a triple bond and a lone pair on each atom, and then that would be good. So this is not a good Lewis structure, and the reason it's not a good Lewis structure is because the carbon atom has the wrong number of electrons around it. So is the proposed Lewis structure reasonable? No. It has the right number of valence electrons, but it doesn't satisfy the octet rule. That is correct. The atom with a problem is carbon. Okay? So that's it, right? So you check both those things in that order, and we found that it was the second thing that was wrong. And so then, the reason that it's wrong is that carbon only has 6 electrons around it. Okay, let's have a look at this one. Draw the Lewis structure for a thiol ion. So the first step in drawing a Lewis structure is to count valence electrons. And remember what we said, for representative elements, the number of valence electrons is equal to the group number for an atom. So the sulfur, it's in group 6A, 6 electrons. Hydrogen's in group 1A, 1 electron. And then we've got 1 more electron for the negative charge. So we have a total of 8 electrons that we're going to use to complete all of the atom's octets. The second step in the process is to identify the central and outer atoms. And what we know is that hydrogen is always an outer atom because hydrogen can only form 1 bond. So sulfur is going to be considered the central atom, and then hydrogen is the outer atom. Now we should put the parentheses in now and put the charge in before we forget. We're going to go ahead and join these 2 atoms together with a single bond because they have to be joined by at least a single bond. A single bond uses 2 electrons, so we'll go ahead and subtract 2 from our total, and that leaves us 6 electrons left to do everything else. Our third step in our process is to complete the octet, or to complete the noble gas, step 3, complete the noble gas configuration of our outer atoms. Now hydrogen is happy with a share of 2 electrons, which it currently has, so we've already done that. And then the next step is to put any remaining electrons as lone pairs on our central atom, which we've done there. And so that uses up the remaining 6 electrons, and we have none left. So we've done that one. Then we have to check that our central atom has an octet. 2, 4, 6, 8. It does, so we don't need to do anything. If it didn't have an octet, we'd have to bring lone pairs in to make double bonds. So that's going to be our structure. That's it. We're all done. So it looks good to me. We know that hydrogen likes to make 1 bond because hydrogen atoms, they have a Lewis dot diagram with just the 1 dot, and so they like to make 1 bond. So this is consistent with that. All right. So we're in business. Okay, let's see what we've got here. Now, do we have, I guess the question is, do we have enough, do all of our electrons add up correctly? We had 8 electrons, remember, so we've got 2, 4, 6, 8. We're using 8, so we know that we're correct. Okay, always worth double checking again and again and again. Okay, this is an interesting one. It's a 2- anion, it's S2-. So what does sulfur look like, just the straight up atom? So sulfur has a Lewis symbol where we have 6 electrons around the sulfur atom because it has, it's in group 6A, it's got 6 valence electrons. So what about if I add 2 electrons? What's that going to look like? Well, what's going to happen is my sulfur is going to fill those 2 octet vacancies, and now it has 4 complete lone pairs around it, but we want to put the 2- sign on the outside there. So there it is there. That's what it's going to look like. In parentheses, the symbol for sulfur, 4 lone pairs, then outside the parentheses, the 2- sign. Pretty straightforward, that one. You just got to not make an error. Okay, draw the Lewis structure for a bromine Br2 molecule. Okay, so here's bromine, and it's in group 7A. So Br2, so we've got 2 bromines, and they're in group 7A, so that means we've got 14 electrons to work with. So we've done our first step, which was count up valence electrons. If you go into chapter 7, and you go into Lewis symbols and Lewis structures, there's a little list of the rules for how to make Lewis structures. Here you go, and I've highlighted it here. Here they are. All right, so you can always just look at that if you aren't great at remembering these rules. But this is something we did in Chemistry 139, and it should be pretty quick to review, and just make sure you can follow through these rules. All right, so the next step is you need to identify what is the central atom. Well, is it bromine or is it bromine? There isn't really, one that's the central in this case. They're both the same type of atom. So we're just going to connect them like that by a single bond. And so that's going to use up 2 of our 14 electrons, isn't it? Right? 14 minus 2. So we've got 12 electrons left to finish everything else off. So I'm just going to pretend that the one on the right is my outer atom. So it's like complete the octet on your outer atom by adding lone pairs. So I'm going to put 6 there. So I'm going to take 6 electrons away and leave 6 electrons remaining. And then it says replace any remaining electrons on your central atom. There we go. So they go there. So that uses up all 6 of them. And then on the central atom, I've got to check whether it has an octet. And if it doesn't, bring in lone pairs until it does. 2, 4, 6, 8. It does, so I'm done. I don't have to do any more there. So that's it. It's just going to end up being a single bond between those 2 guys, which makes sense because bromine has 7 dots around it in its Lewis symbol. It's got 1 octet vacancy, so it loves to make 1 bond. All right, guys, I feel like we moved through this pretty decently. So yeah, I'm pretty happy with how everything went.